Good afternoon, everyone, and welcome back to the 2025 RASC-AL Forum. We're continuing today with the Small Lunar Servicing and Maintenance Robot theme with our team after lunch, Arizona State University, and Diana, Diagnostic and Intelligent Autonomously Navigated Assistant.
Thank you, Victoria. Hello, everybody, and thank you for being here and allowing us to present before you today. We are Project Diana, and we are from Arizona State University. Here's our team structure, where it is broken down into individual areas of research, where each team will have a dedicated sub-team lead, all under the guidance of our faculty advisor, Frederick Garrett, who's here with us today. Here are the topics we'll be discussing in our presentation. We will first go over a mission overview, followed by a series of subsystems that define Diana. We will then go into program logistics, and then a prototype discussion, followed by a closing Q&A. Jumping right in, Diana stands for Diagnostic and Intelligent Autonomously Navigated Assistant. Here's our logo that depicts a robotic arm holding the moon, signifying that Diana aims to conquer the moon through her maintenance and servicing capabilities. In framing the problem, NASA's Artemis mission aims to establish a stable human presence on the moon, wherein a lunar base will be established. This lunar architecture will necessitate maintenance and servicing capabilities to be conducted by astronauts, essentially increasing risk exposure to them. In this competition, there have been a broad list of requirements given to us, allowing us to derive our own requirements and altering our subsystems to allow Diana to directly address reducing astronaut risk by limiting their exposure to the lunar environment.
Our technical approach for Diana's design considered constraints from the lunar environment and the mission objectives. We fixed Diana with a 6 degree of freedom arm with interchangeable end effectors to allow for Diana to have an increased amount of maintenance and servicing options. We also included a robust propulsion system that allows Diana to traverse the rough, very cratered lunar surface at the South Pole. We also have a high energy density lithium sulfur battery and infrared and visible light cameras to allow Diana to monitor her surroundings. Diana's innovative approach includes autonomous driving capabilities and maintenance capabilities, utilizing her LiDAR and radar systems, as well as a satellite map using the Lunar Reconnaissance Orbiter data. Diana will begin her maintenance cycle at her quarters, where she will finish fully charging and receive her task schedule for the cycle. She will select the tools and payloads for the tasks at hand and continue to travel towards the designated location. In this example here, Diana changes a fluid umbilical and completes a diagnostic check before moving on to her next task. Midway through traversing the lunar environment, she gets a manual override command, as there is an urgent, unplanned for, unscheduled maintenance task. In this case, it is a fluid leak where Diana is sent to patch. After completing this task, she then regains autonomous control and traverses to her next location, where she will finish the rest of her scheduled tasks. Afterwards, she then travels back to her quarters to begin charging and await the next maintenance cycle. Here's a list of tasks and protocols that Diana uses to determine her state of being and her power state. A T1 task is a fully autonomous task that requires no astronaut intervention and is going to be the bulk maintenance and servicing tasks Diana will interfere with. A T2 task will be an astronaut monitored task and will be likely a maintenance task, a scheduled maintenance task, where she will be interfacing with a critical life system. A T3 task will be a fully manual override task, much like we saw in the ConOps, where it is typically an unplanned for and unscheduled urgent task. Artemis is planned to be Diana is planned to be deployed in 2040, following the Artemis 7 missions, where there will be a established lunar presence, including infrastructure and a permanent crew rotation. She will be there to facilitate the growth and industry of the lunar infrastructure through maintenance and servicing of existing and future lunar infrastructure.
Diana's propulsion system is inspired by 3 distinct rovers: the Mars Perseverance, the Sherpa by DFKI, a German robotics company seeking to conquer Mars, and the Viper rover. Diana's propulsion system features a variable geometry suspension linkage capable of variable rover envelope for an expanded configuration for increased static stability and a compact configuration for storage. Articulation occurs using transmissions, gearboxes, and electric motors, requiring 3,000 watts per hour for full functionality. Stability analyses indicate that with random placement of the propulsion system and a 50-kilogram mass on the arm, we are well within the stability regime of initial calculations of 230 millimeters, never breaching 181 millimeters shift in center mass. We also did this for a short axis tilt of 40 degrees and a long axis tilt of 40 degrees. Finite element analysis indicates that Diana is capable of supporting 312 kilograms per propulsion unit under lunar gravity. This means that there are no significant stress-strain concentrations, and the propulsion system should last for the entire duration of Diana's lifespan. In its standard configuration, we see a maximum flex of the propulsion system under this 500 Newton load of 1.41 millimeters. With the propulsion system fully integrated into the chassis under a 200 Newton load, which is equivalent to 123 kilograms on the moon, which is a slight increase from our technical report as we added an additional feature to the propulsion system, we see barely any flex and no strain concentrations.
So we want Diana to perform most, if not all, tasks that the astronauts can do on the lunar infrastructure. To do this, we created the Endurance Arm, which combines the GIT-AI arm and effectors, the Perseverance Arm load capabilities, and NASA's Cold Arm thermal capabilities. The Endurance Arm uses an articulated arm framework, which sacrifices speed and power for accuracy. The arm is about 1 meter long, uses 6 degrees of freedom, and can carry up to 45 kilograms fully extended at the tip. The arm can take up to negative 170 to 70 degrees Celsius, and a max power wattage usage of 114 watts.
As stated by Oscar, we will be using the GIT-AI COTS off-the-shelf system. It will be all mechanical and interchangeable as well as modular, so she will be able to change between a multitude of different end effectors for different tasks. It has been tested in a lunar regolith chamber, so it is TRL level 6, and it has a glass coating to repel lunar regolith, as well as a deep learning software that can still recognize the markers even when under dust or shadow. Just an example of some tool sets she might need for any of her tasks on the moon when they are determined fully are strong grabbers, screwdrivers, socket tools, as well as 2 additional arms for removal of dust, such as her EDS arm, which will be externally powered, as well as her N2 gun, which is external as well. She will also have a storage bay in the center of the recessed chassis as seen on the prototype. This will be 3D printed for different configurations that she can choose at the beginning of her maintenance cycle for different storage options you may have to transport, such as solar panels, electronics, umbilicals, or any other mixed payloads.
So dealing with moon dust is a significant problem for astronauts due to its abrasiveness. To deal with this problem, Diana uses passive methods such as Teflon and felt seals, along with laser ablative patterning and ceramic surfacing on the exterior and critical components of Diana. The Teflon seals work by 2 rings that will be placed on the joints and moving mechanical parts, which are close enough to where dust cannot enter. The laser ablative patterning creates a microscopic pattern on the geometry of the surfaces of Diana, and this would also be used on the ceramic surfacing as well, in which the dust that lands on the surface would fall off very easily. In terms of active methods, we'll be using an electrodynamic dust shield as an end effector. This dust shield removes up to 90% of moon dust, and allows Diana to remove dust from specified areas. And along with this, because of this electrodynamic dust shield using quite a bit of power, we're going to have an external power source separately for this end effector. In the case for which the electrodynamic dust shield cannot remove dust from a specific location or the material is not compatible, we would be using an external nitrogen gun that is pressurized so they can get into the crevices and locations that the electrodynamic dust shield cannot reach.
Now, in order to ensure that Diana will be able to survive the harsh lunar radiation, we will incorporate multi-layered shielding. Our chassis will be made of aluminum for its lightweight and durability, while our rover electronics module, or REM box for short, a small box that will encapsulate the critical electronics only, will be made out of tungsten and ultra-high molecular weight polyethylene. We chose tungsten for its density or high density and atomic number, while we chose ultra-high molecular weight polyethylene for its long hydrogen chains, which are excellent for particle deflection. Diana will in course include several radiation hardening techniques. These include silicon-on insulators, triple modular redundancy, error-correcting codes, guard rings, and watchdog timers. These are all industry standard circuit design techniques that will help reduce the possibility and impact of single event upsets, single event latch-ups, and gate ruptures. Now this figure here depicts the expected total ionization dose over time. We made this using the maximum total ionization dose or radiation rating of some of our components, as well as the rough approximation of 60 rad per year on the moon. This equates to 600 millisieverts for reference. In order to verify the validity of our radiation design choices, we used CERN's particle simulation software, GANT4, to replicate the lunar environment. With this, we were able to obtain results for both solar particle events as well as galactic cosmic rays. For each, we ran a multitude of simulations with numerous particles. This allowed us to obtain approximations for the average total ionization dose and average single event upset count. Using particle flux values obtained from CREM 96 and the SPENVIS radiation models, we were able to scale these up to give a better representation of the lunar environment.
Keeping all of Diana's components in their regulated thermal ranges is a difficult task without any atmosphere to keep thermal insulation and convective cooling happening. However, we can mimic these features on Diana herself, using MLI to give Diana greater thermal independence from her surroundings and an internal single-loop heating piping system to heat and cool the larger areas of her internals. We also have capped-on heaters placed on components for individualized heating, and we have Louvre-style radiators produced by ESR Space that have variable heat rejection. These are manufactured specifically with lunar dust in mind. As we can see here on this graph, we have the different kinds of areas that need different thermal attention for Diana. The blue areas are where she doesn't need any thermal regulation. The yellow ones where she only needs heating from the capped-on heaters. And the purple areas where she needs heating and cooling throughout the lunar day and night cycle.
And here we arrive to our command and data handling portion of Diana, where we've opted for a two-computer design. These are currently rated at TRL 9. For non-lunar applications. So the use case is the same for Diana. However, due to the change in environment, that drops to 6 or 8, something that can be improved with further testing. The way it works is the first computer will act as a high processing unit, and the second will act as a preliminary data processor to package the data from peripheral sensors and then feed it to the first computer. The thing back one slide. We will benefit from decreasing the amount of processing demand on one or the other computer, and we will also reap the benefit of the high processing computer having the 64 gigabytes of storage. And here we have a flow chart of our data pathways from individual subsystems, where we also map out the power lines from individual components in these subsystems.
As for Diana's telemetry tracking and communication system, it provides dual-mode architecture for Diana, enabling continuous operations on the lunar surface. The system features experimental free-space optical link implemented through onboard LiDAR sensors, as well as a conventional radio frequency implemented through a software-defined radio. As for the free-space optical feature, it is the innovative feature of Diana and is rated currently at TRL 4. It uses the onboard LiDAR sensors, which will be further discussed in the guidance, navigation, and control centers section for dual-use functionality. This enables us to reduce cost, mass, and complexity of the system because there is no need for a separate acquisition and pointing mechanisms. Using LiDAR for our optical communication also enables us to contribute to the ongoing maturation of laser communications as envisioned under the Artemis program. To build in redundancy, we're also using radio frequency link on an S-band. As for the software-defined radio, it allows us to use encoding and modulation schemes to be configured dynamically. This means that when the link is strong, we can use 16 QAM modulation for that high signal-to-noise ratio. As the link is degrading, we can divert to QPSK or BPSK modulation.
The guidance, navigation, and control system is comprised of three major components. The LiDAR and radar systems will be used to map Diana's near proximity, providing her with collision avoidance capabilities. The satellite imaging component will be used to assist in determining energy-efficient routes for Diana to traverse in her maintenance cycles. This is the current sensor configuration for the LiDAR sensors from the top and side views. Each of the sensors has a field of view of 100 degrees from the top view and 50 degrees from the side view. Do note that on the right, the propulsion systems have been hidden in order to show these fields of view. This is the same sensor configuration except showing the front view. This view also has 50 degrees field of view.
And here we arrive to the software architecture for our GNC system. Please note that this is heavily inspired from research in Carnegie University and Ames Research Center in simultaneous localization and mapping algorithms. Specifically, we aim to employ some type of fast LOAM, LiDAR, odometry, and mapping algorithms, where the way it works is we will feed data from the left-hand side into our embedded processor from our peripheral sensors, which is then fed into the high-performing computer, where there are three different steps of mapping, localizing Diana, and then navigating her to the waypoint. During non-autonomous operations, please note that the only thing that is omitted is drive arcs and forward simulation, since there is no need. The astronauts are going to be controlling her. Additionally, from the left-hand side, one of the sensors that will be used, can be used, is the cameras, where the astronauts don't have to rely on the mapped mesh. Instead, they can visually see where she is going.
As for Diana's payload system, it is designed to monitor the lunar environment as well as aid in her maintenance and servicing tasks. To do so, she will implement 2 visible light narrow-angle cameras, 2 visible light wide-angle cameras, and 2 infrared cameras. To support the operation of visible light cameras during the lunar night, she will also be implementing 2 headlights on her mast, and additionally a ring light on her robotic arm. As for the visible light narrow-angle cameras, Perseverance's Mastcam-Zs have been a heavy inspiration for these components. They will allow Diana to see the effects of moon dust on lunar infrastructure, to then relay to the astronauts for further research and further refinement of her future maintenance tasks. Wide-angle cameras will be mostly used for remote control capabilities. They can provide 8 frames per second and have a 87 degrees horizontal field of view. Infrared cameras are implemented to be able to detect fluid leaks, but they can also support Diana's capability to see the composition of or to research the composition of the lunar surface and its thermophysical properties. To make sure that Diana is fully functional during lunar nights, 2 headlights are implemented on her mast, as aforementioned. Each headlight will deliver up to 2100 lumens and will draw up to 26.4 watts of power. As for the another component of the lighting system, the ring light on the robotic arm, this will enable the robotic arm to see up to 0.6 meters ahead of the arm and will draw up to 3.52 watts of power and deliver up to 280 lumens.
Diana will be utilizing as her main charging system a wireless power transmission architecture. This will be transmitted from the lunar infrastructure as is outlined in the NASA envisioned future priorities. She will capture these microwave beams with standard solar panels that require no custom retrofitting, and then this energy will be routed to her lithium sulfur batteries. The power specifications for this, I chose a Rocket Lab solar cell that is qualified for space, that is used on solar panels in satellites. It has a 33% efficiency. We expect that to get to 40% based on industry standards by the time Diana is launched, as well as a 50% beams transmission from NASA architecture as well, and the charging time should be under about 2 hours. We will also utilize a redundant system of near-field charging using the commercial off-the-shelf Astrobotics system that is currently available right now. It's only available at a 400-watt level, which of course is too small for Diana. So right now, this conservative number of being under 14 hours, and we will need to scale this up in the future.
In order to store this power, we're going to use innovative lithium-sulfur batteries. These have a couple advantages over the typical lithium-ion batteries, mainly that they have higher energy density. They also have higher thermal bands and quicker charging capacity. This does come at the cost of higher development needed for base functionality and lower cycle life, but that isn't as important for Diana as it is for solar-based rovers. With only 22.5 kilograms of battery, we have 9,000 watt-hours of energy storage. As we can see on this graph right here, this is a power cycle for a sample task during lunar night. We're being very liberal with the timing here, so this takes just under 2 hours, and the propulsion system, we're going to be moving for about 70% of that time, which is our largest power driver by far. Even with all those factors and the thermals for lunar night, we're still at over 50% battery capacity by the end of the task.
Here is our current representative risk matrix that currently represents only contains critical risks or risks that have an association to NASA shortfalls. Some of our largest risks were CDH 1, 2, and 3, as well as RAD 1. RAD 1 refers to an electronic failure due to radiation dose, and CDH 2 relates to sensor data corruption. In order to mitigate this, we have implemented multi-layered shielding as well as data correction techniques, or rather RAD hardening techniques. Now, CDH1 and CDH3 refer to the over-delegation of tasks to the onboard computer, which, as discussed previously, we have mitigated using a second processor.
This is a rough breakdown by subsystem, the cost and mass for Diana. As you can see here, our mechanical, power, and CCDH systems are our main drivers for those numbers here. Diana has a total mass of 436.95 kilograms, and our total direct costs are about $361 million. I do want to note that some of these are now estimated using NICM 10 parametric estimates instead of the previous PCEC estimates. Here is our cost by schedule through NASA typical phases. We had a few limiting factors here. We wanted a launch date of 2040, a 15-year lifespan, and we were ending pre-phase A with this study. The costs included on here are integration and testing, direct costs, project management, mission assurance, mission operations, and the launch vehicle. A 30% cost margin was added to the entirety of this.
This is our current prototype chassis and propulsion system. In front of us, you can see our entire prototype. There are a multitude of differences between the current prototype and the full-scale model. First, there's various 3D printed stand-ins to represent instruments and sensors that are just demonstrating location and placement. And then if you refer back to the propulsion system slides, there is a long bar extending through the propulsion system, which is representative of a lead screw. The design has been further refined such that the lead screw no longer protrudes from the propulsion system in any configuration. Additionally, only 4 of the 5 degrees of freedom are present on the prototype, and only 2 of those 5 degrees of freedom have motors for actuation due to time constraints.
In summary, Diana is an excellent choice to address the need for a maintenance and servicing lunar robot through her autonomous systems, which she can achieve with her 6-degree of freedom robotic arm, robust propulsion system, and autonomous architecture to lay a foundation for Moon to Mars missions to come. I'd like to take this time to specifically thank these entities for their funding and contribution to get us our prototype, and specifically individuals Frida Kellgren, Bo Ingram, and our faculty advisor, Fred Garrett. And then I want to thank you for listening, and we're now open to any questions. Thank you.
Thank you so much. That was Arizona State University and Diana. We'll now go to the judging panel for questions, beginning with Chris Jones.
All right. Thank you, Arizona State. Well done on explaining the concept there, and intrigued by the idea of being able to use the LiDAR in a dual purpose mode for a communication system too. I want to go back to the EDS end effector there. You mentioned that there's going to be the separate power supply for it. Where is that located, and how do you then have the energy from that connected to the end effector? And then how much range do you have with the end effector in your arm to reach out and clean things?
Hi, thank you for that question. So we want the external power source on the end effector itself. So there's like there's a model there, but there's some prongs there that are going to be used to like to zap the materials, right? And so that little cylinder thing would represent the battery there. And so we did find that it uses about 2 kilowatts. So that's a little bit of an estimate, but we want that battery that's on top connected to the end effector, and then we want to have where they're connected to have like a switch so that Diana can manually turn on and off the system. Now, in terms of the length, our goal is to use it where, like is a case where we have to get a lot of moon dust that's built up, and we want to use it maybe once or twice a task. But further analysis into that would be our goal to figure out exactly how long we can use that system.
I was going to ask, do you envision that battery being a standalone battery that you can or cannot recharge, or would it kind of be a disposable?
Our goal is to have it to be able to recharge. And so we did not spend, we could have used more time to investigate that area. Just because the battery, that end effector uses a lot of power. Mm-hmm. So our goal is to get it to recharge. If we are using one battery, one and done, that would be kind of wasteful, and we have to figure out where to put it. If we can have something designed where it can recharge, that would be perfect.
Okay, thank you.
All right, yeah, nice job. I wanted to talk here a little bit about your rationale on the chassis configuration there. How was it constructed, just your structural concept, and then do you have any concerns? 'Cause it looks like you have this open storage box design about just long-term regolith collecting in there, and plans to address that.
Thank you for that question, John. We have a variety of storage configurations that we're going to be utilizing, and the regolith has been a concern, but we're hoping that the electrostatic discharge attachment will do most of the heavy lifting in terms of dust mitigation, and then we have a second N2 gun that we're utilizing on base, separate from Diana, as an additional means of clearing dust from the bay, as dust collects, and it's no longer. It's at a volume beyond what we can clear with just the ESD gun.
And on the structural side, you've got these panels. Are they just solid panels? Are they honeycomb, isogrid type structures? What did you use for your mass estimate on that?
First, I'd like to just add a little bit to the previous question.
Oh, sure.
It's not, you can't actually see it in this view here, but there is a slight cutout on the chassis in order to allow for that dust to escape instead of just building in like a permanent storage. As far as structural concerns, that's something that we did a bit of simulation on, and we did find that some of those long panels on there would be potentially a problem, but that's something that we'd have to look further into as far as an isogrid structure or something to add additional strength to the chassis.
Thank you.
All right, good job. I appreciated the presentation, including the timeline in terms of a lunar night, so I thought that was good. So in terms of your navigation, you have both you have a squirrely and the radar, I believe, right? Is that correct?
Yes.
What is the benefit of the radar?
Redundancy.
Just redundancy.
Yes. So in case the LiDAR system fails or the radar system fails, you have that visibility independent navigation method to override that, and you wouldn't be stranded with no means of navigation.
And why, on the power beaming, which is an interesting approach, why is that not a risk in the risk table?
It is a risk in the risk table, I believe. It's just not one that Garrett explicitly mentioned, since I figured I would
Okay.
get some questions about power beaming specifically.
Let's try to find it. Maybe it's there.
Solar panels covered in dust is one of them. They're kind of all spread out throughout the thing, depending on it. But mostly, it has been, I don't know if you know, but they just did testing in March for Starcatcher is doing solar-powered beaming to satellites. So that is a very, upped, I would say, timeline from what was estimated 2 or 3 years ago when I was reading the Vision Future Priorities. So TRL levels have been pushed up, so it's less of a risk than we initially first thought. And then as of March 16th, it's not microwave-based power beaming, but it is laser. DoD just completed a successful test.
I was going to say, why didn't you use laser? And then finally, last question. So something's 4 kilometers away. Something is beaming in the presentation, microwaves to your rover.
Yes.
How is that thing at the infrastructure base tracking
Can you go to my infrastructure backups? So I have this in future research as well, but it is assumed from the lunar infrastructure as the one that has yes. So in the Artemis plan, there is a plan to have power beaming from the rovers, if you see distribution here. So it's going to be fully integrated into the lunar infrastructure. So the pointing acquisition is something that not necessarily Dinah needs to worry about, but whatever system she is servicing.
All right, nice job. Speaking of power beaming,
I'll just stay up here.
sounds good. Did you lay out your ConOps such that if you were out on a mission and you lost your power beaming capability, you have enough get-home power on your batteries to make it?
Yes, so in our ConOps and in our procedures, it's actually that we always stay above 50%, just
Okay.
as a redundancy issue, and to make sure that if anything happens, that we always have 50% to get back to base, which is more than enough.
Okay, so some sort of range limiting, and you also watch your depth of discharge. Got it.
Yes.
And then nice work regarding the discussion on radiation susceptibility and mitigation. The parallel to that on the surface is regolith. Can you tell me a little bit about how you sealed your joints to keep all the nasty regolith out?
Yeah, I can answer that. It's a great question. So what we determined was looking at the model, any joints that would be moving. This is, I think, more so with like the legs here and the arm. Yeah. Our goal is, so let's say let's give an example of a joint that only rotates. This would be representative of the arm. There would be one ring on one side, and then the other ring would be on the other side. Now these rings are going to be extremely close together, but they won't be touching. And what happens is when one joint rotates, the rings are going to allow rotation, but in between those rings, there's going to be a really fancy, super artistic, design where the dust cannot get in because the crevice in between is going to go backwards and forwards.
Okay. All right, and we can talk more at the poster session. Do you have something else?
I do want to add that we will be adding, as the propulsion system kind of reaches its final iteration, we'll be adding a glass fiber mesh system similar to what Viper uses, or whatever Teflon, their Teflon-based fabrics that they're coming out with. So that's an additional layer of mitigation that we have.
Okay, great, thank you.
Yeah, great job. Good concept there. My question is going to be about your cost breakdown. It looked like you as well used NASA's PCEC to do your cost estimate. And when I look at your tables, the way you did it there, it was not. I'm still trying to break it down to what is development costs and what was recurring cost. And even when I went in your backup charts, I was having a hard time. I just want to know what is your development cost and how long did it take?
So NICM. So anything that was estimated with direct costs right here was actually updated to use NICM estimates instead of the PCEC. So the rest of the costs other than direct use PCEC estimates. I can get with you at the technical poster session to break down that development cost according to NICM. I just don't have it listed anywhere here.
Good job. I'll just caution you again about significant digits. And the question that I have is, Diana's mission is 15 years, right? So have you considered, I mean, the 15 years is a long time to be doing anything. So have you considered any evolutionary paths across the 15 years, any additional capability that could be performed by Diana as it reaches its end of life? And when it does reach end of life, what do you do with it?
Well, I know we made mention in our technical paper about additional costs regarding anything we want to add in the future. So we did make that consideration. We just haven't thought of anything specifically.
Okay.
We are mainly focused with just maintenance and servicing tasks that Diana can tackle. And the 15-year lifespan, it is a long time for her to function. But we do think with the current thermal and radiation mitigation, she'll be able to last an entire length. Does that answer your question?
Yeah, but given the last couple of presentations where they're changing out batteries because batteries go dead and so on and so forth, I did not hear that here.
Sure.
Yeah. So lithium sulfur battery technology is pretty new. It's something that I've only seen in liquid battery packs so far. Right now, it is estimated to have a low life cycle, so we would have to replace those every so once in a while. I don't have a number, but I can bring that to the poster session for you tomorrow. I think those batteries, we're going to be putting a lot of money into developing those battery technology, so hopefully we can get that higher. But other than that, I don't believe we have any planned obsolescence, right?
Okay, and what do you do with Diana when her time is over?
I do have a 6-month Phase F closeout phase for Diana on our schedule. That is specifically so that any astronauts who are on the lunar infrastructure can study her and the effects that the lunar regolith and thermal loads and radiation loads had on her. So she can be used as sort of a scientific case study after her death, so to speak.
Okay, so that is the $4 million-ish.
Yeah, that's the personnel cost for studying her there.
Okay.
Yeah. And once she's done being studied, I do know that Artemis, since this is what we're planning on being in partnership with, has a disposal method system that they will either have waste either staying on the moon or some type of method to bring it back to Earth, but that is obviously up to the lunar infrastructure and whatever the astronauts decide to do with her, not necessarily part of our mission.
Thank you.
All right, I actually have 4 questions, but I'm just going to spend 2 minutes asking them. If we don't get to the end of them, I'll pass it on to Amanda here. Quick question, what is the scale of your prototype?
I forgot to mention that. It's 50% scale,
50%,
this guy right here.
okay.
Thank you.
That's one, okay, that's 15 seconds. How does your full-scale version get to the moon, and did you include that in your cost?
Jarek, is it included in our cost?
That's the launch vehicle cost right there in Phase D.
Okay, and what's it launched on?
It's going to be launched using the CLPS, which is the commercial
CLIPS.
lunar, yes, CLIPS system. So we basically decided that using the CLIPS system, we will design Diana to our own specifications, and then we will put it up for a bid, and then whichever lander and yes, whatever flight system chooses to bid on her will be able to fit to our specifications. I have checked that all of the current CLPS providers, Diana can fit in their fairings with no problem.
Fantastic, and what was the cost you assumed for that?
I don't have the number off the top of my head there, but I believe it's around 100 million, 120 million for
Okay,
Diana.
it's the right number of digits. Okay, good,
Yeah.
good. Okay, all right. That's what I care about. That's
It was
what I care
about
about.
300 per kilogram, right?
It's launching is more than the rover a lot of times. Okay, one more question, then I'll give it to you. I've bugged everyone else about this. I'm going to bug you guys about it. I see a rover that does servicing with one arm as a major risk. All right? All right. Tell me what I should know.
All right, as of right now, we chose such a complicated arm and end effector system that we imagine that Diana is going to be able to do it with an arm, but that is something that in the future that we've thought about perhaps adding, since we do have extra budget in our mass.
All right, so homework, when we get to the poster session, I want you to tell me how you would do umbilical connections, because it's really sort of lightly covered in your paper.
Yes.
In detail with one arm and two.
Okay.
All right, thank you.
Thanks. I'm having trouble understanding how your GN2 gun's working. Where is the GN2 stored? How's it replenished? What's the mechanism that actually pushes GN2 through?
Oh, N2. Okay, so the
Is it-
N2
is it
gun.
not
Yep.
GN2?
No, it's gaseous.
Is it gas or is it GN2?
Oscar gas, right?
So yeah, so not just air.
Yeah,
GN2.
gaseous. Guys, they're all whispering to me. No, so as we've decided that adding another fluid system to Diana would complicate her, it's going to be in her garage where we can switch out her end effectors, and she's going to have that external N2 gun that she simply can control and connect to, but it will be like a full canister, something similar to what an astronaut would use if they were using an N2 gun, which she can do with the
So you
dexterity.
get one spray. How's it work, right? Because you have like,
That is something that we have not fully determined or researched. It is something that is in our future development. We have decided that since we don't, somebody else, yes. Perfect.
It wouldn't necessarily be just one spray. The way her arm works, well, this specific one, it's more of like a claw, so she can actuate it and depress whenever she doesn't use it. So it will run out at some point, but like Kylie mentioned, there will be a storage compartment, or I should say quarters, on the base where Diana can store her tools, and that's where she's going to be accessing them and putting it back from.
Okay, so you're gonna somebody's gonna bring these GN2 canisters along.
I think the lapse here is the canister is going to be located on the end effector itself. So the fluid would just have to be replenished in the end effector, but she'll be able to autonomously go grab that end effector and use it.
Okay, thank you.
Yeah. That was one of my many questions. So nice concept, nice pictorial view of what you're doing, but I didn't see any details on any of the subsystems in terms of mass, power, dimensions, and performance. So you had a lot of room on the charts to provide at least a summary of that. This is cost.
This is cost and mass for
Okay.
each subsystem.
Okay, that
so
helps.
We got one of them.
That helps. But will some of the cooling areas that you mentioned, or areas that only needed cooling, will they get overheated in the sunlight? And how do you deal with that? Or did you think about that?
Yeah, so that's why we have the single loop heating piping system. That's going to be Freon 11, just like Perseverance has. That's a really low power system. Their
Right.
pump handled 2,000 watts of thermal energy constantly at only a 10-watt pump.
Okay. And how do solar panels convert radio frequency waves into electricity?
So that is something that currently is proprietary technology and I do not have access to. Starcatcher essentially is a commercial company that is looking to basically privatize and sell lunar power beaming. So, and there's more than one company that is doing said power beaming in there right now. It's currently at a TRL4, and then the tests recently have been TRL6, but I've done so much research into it, and as of right now, I haven't been able to access exactly how they do it. They just say they can do it, which obviously we have, it's 2040 until then to figure it out, but we would be contracting out with them for that part.
And then what defined the 65 gigabit storage capacity?
That's part of the main computer. It just features that non-volatile flash memory.
Well, so do you know how much you need between communication opportunities?
No, only because there have been different types of LiDAR-based GNC systems that will map onto a mesh. So I've seen anywhere between like 10 up to 100. So it definitely increases in order. But we're thinking 64 would be enough to kind of backlog the data she cannot transmit. Because one of the things we will be doing is transmitting constantly as she's moving. So she's not going to need to use up all of that.
And then given time and nobody else, how does Diana know where it is on the surface?
Well, one of the sensors we do want to use is GPS. We know one of the recent missions has been successful in demonstrating GPS, so we're expecting by 2040 she'll have that full capability. Additionally, we do have other sensors like MEMS, IMUs, gyroscopes, so she'll be able to localize herself with respect to that mesh.
All right, thank you.
Other quick questions from the panel? Dan? It's on.
Yeah, thanks, guys. Question on the glass coating. Glass gets real brittle in cold, and I looked up the particular coating you're looking at, and it doesn't look like it's going to be applicable in the temperature range on the moon. So.
Yes, so this is the GIT AI arm glass coating that they have tested in a lunar chamber, and so that is something that I think as of 2 weeks ago, they actually just got a contract with JAXA to take one of their arms up to the moon and test it. So this is something that's been tested for TRL-6 in a lunar simulated chamber on a rover.
What temperature range does it go down to?
I am unaware of that currently, but I can
Okay.
get to you that at the poster session.
Okay, great, thanks.
All right. Any yes or no questions from our panel?
I got the impression from what I heard that the team, or I inferred from what I heard, that kilograms on the moon are different than kilograms on the Earth. Is that true, or how did I mishear?
That was a misspeak on my behest. I apologize. Kilograms on the moon are the same as on the Earth. It's the weight that's different. That was a misstep on my part.
Okay,
I apologize.
Yeah. Got to watch. Yeah.
Yep, units.
Yep. Units. Thank you.
And thank you, Arizona State University. That was Diana, and we will be returning at 2:20 with the last presentation of the day from South Dakota State University, NOVA.